has 2 screws connected to the beam, or the post, and 2 screws to the beam. So we are pulling with 4 screws from the beam and 4 screws from the post. We had this discussion with Max. So the screws are sitting like this, right? Everybody see that? So they're sitting like this on the top part and the bottom part like this. So what is your angle to the grain in the beam or in the post?
45.
So that's 45, and in the beam
45.
it's so intuitive. It's 90. It's always to the grain. So the grain is running this way. If I put the screw in here, it doesn't really matter what angle they're in. It's 90 degrees to the grain. So we should have a larger withdrawal resistance in the beam because the screw is at 90 degrees than we have in the post where it's at 45 degrees. And since the embedment is slightly larger in the side member, the expected failure mode would be pull out of the post.
But you wouldn't get the same result for this way in the bottom member, would you?
No, you should. So the question is, if I pull this screw out this way, or this way, or this way, I should get exactly the same value.
Correct, but if you put the bottom ones straight in.
No, then of course not. Yeah,
You said 90 degrees, doesn't matter which direction. I'm just trying to clarify.
No. So that a good point. So if I just pull out the screw out of the beam, it doesn't matter what angle. In this application, because the load is coming this way, the shallower the angle, the higher my resistance would be.
The component in this direction.
Because the component in that direction would be larger. So the larger my angle against the force component, the more I load my screw in shear and the less I load it in withdrawal. So ideally the product approval allows us to go to 30 degrees. So the highest utilization of the withdrawal capacity we would get at an angle of 30 degrees.
Multiple connections that's happening at the same time.
Yes. Yes, we have. I think Max said he thought it might be as high as 40,000 pounds. So we may not succeed in this one, or we may lose our feet. Normally we have the rods aiding us to keep the feet together. In this case, because of the width of the member, we had to pull those rods back. So we have it marked. So if it starts to slip, we'll know.
These screws are fully threaded?
If you have an application with a side in the middle member, you want to use fully threaded screws because otherwise the part that's not fully threaded doesn't give you any withdrawal.
We have screws both in shear and in tension. We have screws that run through the legs and into a horizontal member.
What's your goal?
Getting some crushing there.
Why don't we just pause to consider that?
But by now you definitely have every single screw fully activated, so there's absolutely no doubt that
Whoa, there goes. Something went. 39,000 made. Boy, that was.
They're both sides of the split.
So was that loaded?
39,100 pounds.
Don't know what I lost there.
Good load on that.
Okay, good. You got my arms.
So again,
Picture of that, so we've got the.
as I mentioned in the talk, so in the end we're pulling the same beam against the same post, and we had like how many rivets and how, like if you ever drive in a rivet, it's not as fun.
Screws are way more fun, let me tell you.
A bolted connection.
On my holidays, I drive screws.
All the hardware you need for a bolted connection, and then like the much lower performance. So like in the end, how many screws do we have in here? 16? No, 8.
Well, it's 8.
8 on both sides. 8 per face. So you got 16 screws. Yeah.
4.
Yeah. So it's 16 screws, which probably takes you less than 10 minutes. Or
Yeah. You know, on this one, we do a little demonstration where we take a 6x8, notched 50% on the end, set it on the ledge, and just put it on so each end is resting. It's 50% notched. You know where it's going to break. We break it right here. We clamp it back together, put two 6-inch fully threaded screws in, put the ram back in, break it here, clamp it together, put two fully screws in, put the ram back on, and break it right in the center. And break the beam, and they're getting full capacity. So we're able to use it to reinforce. That's where it's used a lot. Is if you screwed up, if you've got somebody, the plumbers come by and cut this slightly oversized hole in the middle of your beam where he wasn't supposed to. Talk to Max and look at it. You might actually be able to save that guy with fully threaded screws surrounding it and getting force flow around that hole. We're doing that on a project for Synovus right now where they didn't actually have the mechanical guys show up on site until we had the building completed. They're going around laying out huge openings through beams. Saying, no, I don't think that's going to happen, but we just insisted, the openings they have allowed, we want fully threaded screws at each end of it because it's just insurance against split running and just keeping that. It's pretty amazing what you can do with those fully threaded screws.
I'd like to point out too that the cost of the screws relative to connectors, particularly weldments that you have made, are considerably less. Just for the value of the cost of the screw themselves, it's much less money.
And like the one thing to keep in mind is that it's also very, very stiff. Well, it's two things. It's a very stiff connection, right? So we got to this load that's much higher than anything else we tested at a deformation of less than 0.1 inch, right? We started at
Less than 1 inch.
Less than 1 inch.
it started at 7.75 and it broke at 7, so 0.2 inch, 0.2 inch deformation. But it was a very brittle failure. So with this arrangement, there's no ductility. So again, if considering Ghassan's talk this morning, if you want to rely on your metal fasteners to get ductility, then you should not entirely rely on screws and withdrawal.
But do we ever?
So
we
the
need
wood
this,
connection.
Sorry, the connection is designed for 74 kilonewton in total, and we reach like 178 or whatever 40,000 pounds is, right? So.
Yeah, no, but
will we ever reach this low to rely on
design
ductility?
fuse. That's the only thing. Like it should not be your seismic design fuse, because for that it's so stiff and strong. And
If you use the steel plate, though, if you make your connections with the steel plate involved, like with the washers and the steel plates, you can design a fusible connection. So it's possible to design it that way.
You could add some that are perpendicular, completely straight, and then it'll become like you put some in 45 and then some in.
Yeah, except the ones in Withdrawal have got so much more capacity than the ones in.
You
wouldn't even use the straight ones.
You wouldn't,
No,
yeah.
it's going to cut right, strip right
Yeah,
through.
you'd have, the first ones that.
no, well, Max is. We are looking into exactly that. We should be able to actually design a joint. You would need a whole lot of more screws and shear that have a similar capacity, that would not contribute anything until the screws in Withdrawal fail, and then you would have the screws and shear that would pick up the load and would be very, very ductile. So that.
But you have to really tune that, and doing that at design level is going to be tricky if the screw that you designed in 45 is actually three times the capacity. Now that one is done, and you're loading the shear screws that can take half of that, and
Especially if you're at a very high level.
Yeah.
Now all those screws are taking that high level.
Well, you have to design the screws in tension so that they pull out and release the load slowly to the screws and shear. You cannot design the connection in a way that you reach the tensile capacity of the screws and you get a sudden failure, right? You have to design a connection that you pull the screws out and then release the load slowly to the shear screws, right?
So one thing that we did not consider at all was the brittle failure of the side membrane.
Well, this is because it rotated slightly, right? So it gets a
So
little bit of a
this is
bending
not
moment.
the expected failure for a connection.
What was the design level? I mean, just to compare with the roughly 40,000. we get
Around
here,
37 kilonewton. It's somewhere in the design notes there. There's a full
37.
design calculation. I think it was
When that reached
37.
172 kilonewtons or something like that.
Say
So
that
we
again.
got like 37 versus 170, so we got like 4.5 times the design capacity.
And we would have gone higher if we
Yeah,
didn't split.
this is 177 kilonewton and was designed for around
We
37.
wouldn't have.
No, no, but
We would have stopped.
technically.